What's up, guys? So, this is Sir Ernest, and today we're going to talk about energy in a central force field. But before we proceed, let's have a brief recap of what we need to know about central forces. So, as you recall, central forces are forces that follows Newton's third law of motion, the strong form. So, if you have a particle subject to a central force, okay, and that particle is moving with the velocity v and defined in terms of its position with r. So this central force, because F and R are in lie along the same line, therefore the torque caused by therefore the central force will not cause no torque on your particle. So the consequence of that zero torque is that your angular momentum is conserved. Okay, so the magnitude of angular momentum is the absolute value of r cross mv, where r is the position vector, v has two components, that's your radial component and your transverse component. Okay, so computing for the magnitude, we end up with mr squared theta dot, and this is a constant. The direction of your angular momentum points using the cross product between r and p. Okay, so also we define the angular momentum per unit mass, that's L, and that is equal to r squared theta dot, and that is a constant as well. Or from here we can define, or we can write theta dot in terms of L and r squared. So from here we can actually calculate the differential equation of the orbit of a particle moving under this central force field, and that is equal to this equation. That's the second derivative of u with respect to theta plus u equals negative 1 over ml squared u squared times the force function in terms of 1 over u, where 1 over u is equal to r, or u is the reciprocal of r. Okay, now in order to get the energy in central force field, let us first recall what is energy. So we know that energy, or in this case, in our context, the total mechanical energy is just the sum of the kinetic energy and the potential energy. So we know for a fact that kinetic energy, which is T, is given by 1 over 2, or 1/2 mv squared. Because, so remember here, the velocity has two components, that's the radial and the transverse component, and that velocity is equal to this. So therefore, the square of the magnitude of the velocity is just the Pythagorean theorem, and that is equal to r dot squared plus r squared theta dot squared. Okay, so therefore kinetic energy is now rewritten as 1/2 times m times r dot squared plus r squared theta dot squared. Okay, so therefore the total energy, which is equal to the sum of the kinetic energy plus your potential energy, so this is equal to 1 over 2 m times r dot squared plus r squared theta dot squared plus your potential energy function. And because our force function is a function of r, so therefore the associated force, and the associated potential energy with that force, is also a function of r. And because of that, we know that the central force is a conservative force. So what does it mean? It means that the total mechanical energy of the system is conserved. Okay? So now, let's express this in terms, let's express r and r squared, r dot and r in terms of u. So because since we define r to be 1 over u, or u is defined to be 1 over r. So therefore, the time derivative r dot is equal to negative 1 over u squared times the derivative of u with respect to time, or simply u dot. Okay, so by chain rule, this is now equal to negative 1 over u squared times derivative of theta with respect to time times derivative of u with respect to theta, or simply negative 1 over u squared theta dot derivative of u with respect to theta. So from our definition, we know that, remember that L is equal to r squared theta dot. So that means L is equal to 1 over u squared theta dot, or theta dot divided by u squared. So therefore, r dot is now equal to negative L times derivative of u with respect to theta. So therefore, we can now rewrite the total energy in terms of u, where the total energy is now equal to 1/2 m times r dot is this one, and so we square this, so this is L squared times the square of the derivative of u with respect to theta, plus r squared is 1 over u squared times theta dot squared is equal to theta dot squared is equal to L squared u to the 4th plus your potential energy in terms of 1 over u. This should be 1 over u. Okay, so therefore, the energy function E, or the energy equation of the orbit, is 1 over 2, or 1/2 ml squared times derivative of u with respect to theta squared plus u squared plus u, which can be a function of 1 over u. Therefore, this is now what we call the energy equation of the orbit. Okay, so in the next video, we are going to apply this to the problem we had earlier, wherein the particle in a central force field moves in a spiral orbit. So that's r equals c theta squared. Okay, so for the meantime, relax, and I'll see you again in the next video. Thank you for watching. Bye-bye.